We now move to the condensed matter regime with a talk from Marcus Newton from the University of Southampton. Marcus.
Okay, thank you all, everyone. And I'm Marcus Newton, as mentioned before, from Southampton University, and I was representing the quantum materials and nanotechnology section. Where's this? Oh, excellent. So not alone. So we wrote that section also with Anna Goods at UCL, Mark Dean, Brooke Haven, Simon Wall, and Anna Hurst, and Ian Robinson, and also from the community. So we did solicit quite a lot of interest from the community within the UK and beyond. Okay, so what I want to do is go through the main topic itself, the aims, objectives of the division, and also look at some highlights of the science, and then talk about what we would see and what we'd like to see in an XFEL. So our aim is to understand why quantum materials possess the novel properties that they do. We'd like to determine how to manipulate and observe the observed novel properties. Oops. And then with the insight gained, infer how then to induce those novel phases in quantum materials with technological applications in mind. Also, along the way, we want to discover new physics and deepen our understanding of how materials function. So that's our aim as a whole. So what might an XFEL bring to the table for this community? Well, considering we require the ability to track energy flows in quantum materials, so how they change, following strategic pumping often into a state that's not a ground state, of course, an excited state, the XFEL will bring a time domain probe of quantum materials able to resolve fluctuations relevant for deciphering the material's function. That's a mouthful. Sorry. And a means to measure and interpret high-order correlation functions related to those quantum materials. Okay, so I've divided our division into major themes, into a number of major themes, and that's because it's quite diverse, the field. And so I'll start by talking about ultrafast magnetism and move on to the others. And so currently we typically measure a simple order parameter, so the magnetic order, magnetization, for example. But if we had an XFEL, we could look at ultrafast resonant X-ray scattering, for example, to couple to spin orbit degrees of freedom, for example, excited states, order disorder, hidden phases, for example, and look at time-varying characteristics of magnetic domains, so their size and migration throughout a material. Structural dynamics and light-induced phases in quantum materials. So we'd like to learn how light mediates changes in atomic displacements, typically on the picometer scale. So further insights into charge density wave instability. So understanding their behavior, their origin, ubiquity, and also the relationship to superconductivity and how they interact with one another. In terms of imaging dynamics in nanomaterials, we want to observe subtle changes in structure due to external excitation. And the reason why that's important is because often when we're trying to study nanomaterials, we want to see how they behave as they are alone, but also inside of an embedded structure. It's usually quite important. And this is quite amenable to time domain measurements, typically if we're using techniques such as CDI, coherent diffraction imaging. We also want to image structural phase transitions as well in 3 dimensions, if possible. And in addition, we'd like to look at electronic dynamics in quantum materials, and this is largely photoemission spectroscopy, so probing in momentum space, electronic structure, and looking at electron-electron interactions. And order and disorder in quantum materials, so looking at orbital degeneracy lifting, probing local order using time-resolved PDF measurements, so pair distribution function measurements. And that's quite important for looking at materials that have nematic phases, for example, so it could be strontium rutheniates or bilayers of graphene. Okay, so here are some highlights on the ultrafast magnetism region. Okay, so this was an early study that was performed looking at strontium, an early study looking at strontium material here, sorry. Okay, so time-resolved RIC study looking at a strontium material strontium iridate, that's the material. And what they did was perform a RIX measurement on the material, looking at a grazing incidence study of the material, and observed the energy loss, as you can see here. Oops, not behaving for me, sorry. The energy loss is shown here from the measurement, and you can see that they're able to resolve the time varying energy loss as a function here of the pump probe delay. You can see after 2 picoseconds, they can see some variation in the energy loss, and also here. And this is a resonant technique, of course. At the moment, this is got 2 picosecond time resolution, but would like to go to much higher resolution if possible. This is pumping with the mid-infrared, but would also like to look at the full range of different pumps if possible as well, X-ray probe. Now, there's quite a significant RIX community in the UK, particularly at Diamond, I think at I-11. And so this would be well received if we had such a facility at an XFEL in the UK. There's also quite there are a couple of beam lines being developed, I think, at LCLS and also at the European XFEL, specifically for this technique. Okay, moving on. Here we have a important study with strontium titanate here. So this is Keith Nielsen's study at MIT. And this isn't using XFEL X-ray probe. In this case, it's using a 800 nanometer probe. But the main point is that it was a very early study, which was able to reveal some of the interesting properties of this particular material. So they have a paraelectric strontium titanate material. We're able to look at the ferroelectric transient state by pumping into this state with a visible laser. The main point here was that we're able to see a renormalization of the phonon modes to reveal this hidden phase effectively. And so you could imagine this being extended into the X-ray regime. This was an early important study, which was impetus for further work looking at the X-ray properties, the properties using an X-ray source. On the right-hand side here, we have another study more recently performed looking at superconductivity in this yttrium barium copper oxide material. And in this case, we're actually probing with X-rays. And so we pump with an optical laser, and we probe, and we simultaneously look at the charge density wave order and also superconductivity in the material. And the main result was the ability to be able to see how superconductivity and charge density waves interact with one another, and how you're able to quench selectively certain modes to reveal that interaction. And that was quite key. Okay, so moving on to imaging dynamics in nanomaterials. And so here, this work mostly focuses on CDI, so Bragg CDI imaging of a single nanocrystal. And what they've done here is pumped with a 800 nanometer laser and probed with the X-rays, and performed a diffraction experiment looking at various diffraction patterns in 3 dimensions of the time delay as a function of time delay on a single crystal, and then reconstructed as a result. So you can see the reconstructed crystals here as a function of time delay, and they're also able to observe acoustic phonon modes as a result. So you can see the different acoustic modes here. And so this is a nice method. You can imagine, again, looking at embedded structures, again, because of course the interface is the device, so understanding how these crystals would behave when embedded inside of the structure would be helpful for device applications. And so what we'd like to see is high resolution here, time resolution as well, to look at the initial stages of this process and how it continues through time. This study was performed on a simple metal, but we'd like to see how these could be extended to looking at more complex oxides as well. So looking at, for example, vanadium dioxide, which has a ultra-fast structural phase transition. So being able to see the initial stages on the attosecond timescale, and then how it propagates through, would help us to develop next generation technologies. Okay, so electronic dynamics in quantum materials. So understanding effectively how electrons interact in such materials using time-resolved momentum space measurements, so angle-resolved photoemission spectroscopy mainly. And in this particular study, they're looking at layered charge density wave compounds. And so this is titanium, selenium, and so on, and sulfide. And the main aim here is to look at charge ordering dynamics of charge density waves. and the contributions of electron-electron interactions. And so to be able to see their interactions, you want to go down to the attosecond timescale if possible. Finally, I want to talk about disorder in quantum materials. And so this is a study performed by David Keane and Andrew Goodwin. And here we're looking at effectively pair distribution relations between atoms inside of various materials. So here, this is a neutron study actually on barium titanate, but this study here was performed using X-rays. And the advantage of PDF measurements is that you can look at any material, so effectively disorder in any material. It doesn't have to be regularly structured. And what we're able to reveal here is local disorder in the material. So as I mentioned before, if there's pneumatic phases in the material, for example, you can reveal this using such techniques. The challenge here is actually the need. So having high energy X-rays, so up to or beyond 25 keV are necessary to achieve this. And we could do so using the third or fifth harmonic of an XFEL. We also require high rep rates and typically a wide area detector to capture all those different orders. So that's a challenge. And the stability of the XFEL is critical. Does that keep happening? Okay, so just to summarize the outstanding challenges, so ultra-fast magnetism. So we would like a femtosecond or attosecond pump probe scheme in the terahertz, going from terahertz actually all the way up to visible if possible, to couple to phonon modes and then also to electrons. Intrinsic timing would be advantageous if we have it. So that would mean entirely different FEL designs, so being able to access attosecond timing rather than using something such as a cross-correlation technique, you can use the intrinsic timing of the actual machine itself. Going back to structural dynamics and light-induced phases in quantum materials, observe atomic structure on the appropriate timescale. So again, this technique or techniques that aim to do so lend themselves very nicely to CDI measurements as well. So being able to look in 3 dimensions of structure. Imaging dynamics and nanomaterials, so high spatial and temporal coherence would be great. Femtosecond or attosecond timing as well, for us to be able to probe unambiguously initial and final stages of structural phase transitions, and also extend this to complex materials. And for electronic dynamics in quantum materials, so access to electronic dynamics on the attosecond timescale is the key thing here. And an intrinsically timed FEL would again facilitate. And for disorder in quantum materials, using PDF measurements, we want something with high energy, so up to 50 keV, and a wide beam as well, up to 1 millimeter squared for powder averaging. Okay, so here's the summary of our requirements. So we want energies from 200 EV, so it's the carbon K edge, up to 15 keV, typically for most measurements. So the time result PDF measurements are slightly different, so the requirements are somewhat distinct, and so we have to think about whether we want to incorporate that into our design of a FEL, or whether we want to internationalize and perhaps use another facility or buy into another facility to enable this technology, this technique, sorry, within our repertoire. So the rep rate, a few kilohertz typically. For photo emission measurements, we want, that's not great. Not sure what happened though. It's not been easy for me, has it? It just hasn't. Okay, let me go back. We'll survive, we will. Okay. All right, okay, so what was I saying? Yeah, so rep rate, a few kilohertz, for photo emission measurements, megahertz, if possible. Photon pulses, so above 10 to the 10, so not too demanding, 10 to the 10 is quite modest, photons per pulse. So the pump source, as I mentioned before, tunable from the terahertz all the way up to the visible, with femtosecond timing, possible sub-femtosecond timing. And this is quite unique here, so if possible, as I mentioned before, I alluded to this, but the diagram probably will help you to understand a bit better. So pump probe timing with 2 colors, and intrinsic timing, meaning that we get both the pump and the probe from the FEL, rather than them being from a separate oscillator somewhere else in the building. And so that should allow us to get below femtosecond timing and have a truly world-leading designer. And with that, I will end. Thank you.